John, you're live. You can go.
Okay. I'm Tom Dietterich, and I'm a professor at Oregon State University and have the opportunity today to talk to you about machine learning opportunities and challenges. So machine learning is a set of technologies for creating computer programs from data. As I'm sure all of you know, the usual way that we create software is by programming it by hand, step by step. But with machine learning, we instead collect a set of training examples. And I've given some examples of examples over here on the left. These are images of handwritten digits, and then the corresponding output that we would like a computer program to produce. So when we show it a picture of the digit 4, we want it to output the digit 4. And we give these kind of training data to a machine learning algorithm, and it outputs another program. And that learned program, which often has a form of a neural network these days, given a new digit 2, it can produce the desired digit 2. And of course, this technique has been used for much more than just recognizing digits. It's the technology that is underlying recent advances in speech understanding, in language translation, and the internet search tools all use machine learning very heavily. So in this talk, what I want to do is talk to you a bit about some of the new opportunities for using machine learning that are beyond the kinds of things that the internet giant companies are doing, and more focused on trying to reboot the world, as we're saying today. So the talk is in two parts. First, I will talk about machine learning problems in sustainable development, and then I will talk about some of the challenges that we have with machine learning going forward. Problems in sustainable development, of course, in countries with poor resources, we typically need to do three things. We want to collect better data so that we can make better decisions. We want to compensate for the lack of experts, and we want to allocate scarce resources. And I should add that this is true also for the developed world. So these are the three key things that machine learning can help us do in sustainable development. So one project that I'm involved with is called TAMO, the Trans-African Hydrometeorological Observatory. TAMO is a nonprofit startup company whose goal is to transfer Africa from being one of the most poorly sensed continents to one of the best sensed when it comes to weather data. So this is a map where the dots correspond to weather stations that regularly report their data to the World Meteorological Organization. The WMO is one of the United Nations specialized agencies, and it's responsible for setting worldwide standards in weather data. And so these dots, the blue ones are weather stations that reliably send in their data, and the red ones are silent stations. And you can see that there are big gaps in Latin America and in Africa, with a few exceptions. You know, Argentina, South Africa are doing fine, but there are large gaps elsewhere. So TAMO has set its goal to deploy and operate a network of 20,000 automated weather stations throughout all of sub-Saharan Africa. And we've been operating for a few years, and we now have 526 stations deployed in Africa, which is already more than many countries have, even in the developed world. If any of you are entrepreneurs and have some thoughts about how you could create business models around weather data, we'd be very interested in talking to you, because that is why we exist, is to try to create data. Obviously, the data are being used for climate studies and for weather forecasting, but there are many other applications of weather data. A big challenge in operating a weather network is that weather sensors fail. The solar radiation sensor can get dirty, the rain gauge can be obstructed, and we also get novel failures. As you can see here, this is a picture of one of our data loggers where a set of ants decided to take up and turn it into their house. And needless to say, that didn't do very much good for our data. So the work that I do is on artificial intelligence for quality control. We train machine learning techniques to recognize abnormal sensor readings. It might be something like that there's no rainfall at one station when all of the neighboring stations reported rain, or a sudden drop in temperature like this. And then we issue alarms and then technician to make repairs. Another project that I'm not involved in, but was published by Reichmann et al. In Science Advances 4 years ago, is about trying to do better monitoring for dengue fever. So the goal is to detect dengue outbreaks very early and then prioritize interventions such as more garbage collection, removing leaks in the sewer system, spraying for insects. And the data they get is people who are calling health and awareness. So the idea is, if many people, if there's a big increase in the phone calls into the symptom hotline, then maybe that is a sign of disease, of an outbreak. However, it could be a sign that a hotline awareness campaign is being successful and people are just calling in because they saw the advertising. So, but here's some data that they show that the red curve here is the hotline reports. This is a timeline, and the black cases are hospital reports. The green dots are people who are calling in, who actually were hotline awareness events. So you can see that they need to, there are correlations among all three of these signals. But here's what their forecasting model can then do. The red curves are their forecasts from machine learning. The black curves are the hospital reports. So they're doing a very good job. Another, as I said, the second kind of scenario is a need to compensate for a lack of experts. Malaria, of course, is a very serious disease worldwide, and especially in equatorial Africa. The gold standard for diagnosing it is to examine a blood smear in a microscope. But there is a lack of trained personnel to be able to do this test correctly. So people are investigating the possibility of using computer vision to do this, and several R&D groups around the world have been developing methods based on cell phone technology, because, of course, our modern cell phones have very sophisticated cameras and now even built-in neural network computing. So here are the computer vision performance for several of the most recent systems, and compared to a WHO level 1 expert, so a human, an excellent human. And we are looking at how much blood does the test require, and what is the smallest number of parasites that need to be in that blood per microliter in order for it to be detected by the technique. So some techniques can use very little blood, but the 12,000 there almost match the human expert. They see a little bit of blood in the sample, the human, but it's 100. Sustainable develops more into law enforcement, and in particular to anti-poaching in national parks. This is work by Fei Fang and her colleagues at University of Southern California and Carnegie Mellon University and Harvard University. In this case, the scarce resource is game wardens who patrol wild areas in these parks, attempting to catch poachers. And machine learning is used to predict the motion of the animals, say the movement of, say, lions or elephants or rhinoceros, and also to predict the behavior of the poachers. And then to solve what's known as a security game. So there's an area in mathematics called game theory, right, in which you can consider the moves that the poachers might make, the move the police might make, and so on. And using AI technology, they plan patrol routes that are easy for the officers to follow, but are also very hard to predict for the poachers. And this was tested in Uganda and has been deployed in Malaysia. It's also been deployed in the United States for air passenger security at Los Angeles Airport, for the US Coast Guard in the New York and San Francisco and Boston harbors, and so on and so forth. Okay, so to summarize the first half of this presentation, then, I've talked about three roles for machine learning in these situations. One is helping with instrumentation to collect better data for better decisions, to get weather data or to forecast dengue outbreaks. The second is to compensate for lack of experts, and I gave the example of point-of-care malaria diagnosis. And the third is allocating scarce resources, in this case, security games for law enforcement. So now I want to move on and talk about the challenges for machine learning. And there are really three challenges. First, machine learning needs large amounts of labeled data. And this is particularly true when we're working on computer vision type tasks, because you can imagine in a 5 megapixel image, there are actually 5 million pixels, which means actually 15 million numbers that represent that image. And those numbers could be capturing a lot of different things than the thing you really want to be measuring. The second thing I want to talk about is the need for the data to be representative. There's a problem with data selection bias when our data doesn't cover all of the different cases that need to be covered. And the third is a fundamental problem that I call majority bias. If you go out and randomly sample the population of a country, you will get more samples for the majority population and less for the minorities. In the United States, you would get a lot more white people of European ancestry. In Africa, you would get a lot more black people of African ancestry. And you will get very different results from a machine learning system when you sample that way. So let's talk more about training data. So getting data requires obviously access to the data itself, but then training data needs labels. So people have to have enough knowledge to label the data. And what do I mean by that? Well, one of the most influential projects in computer vision is ImageNet, which was developed by Fei-Fei Li at Stanford University and her collaborators. And they got their access to the data by scraping the internet and just pulling images off of various web pages. And I've shown two of the images that they extracted. And then to label the data, they wanted to label each of these images with something like, these people are participating in sport, particularly in a form of rowing and in particular sculling, which I don't think is, I think those folks in the top picture are actually maybe in a kayak. But in any case, then they gave these images to ordinary people on Amazon Mechanical Turk. And the idea or the hope was that most adults have the knowledge necessary to know what rowing and sculling are. And so they were able to get labels from them. But now a case that people are very interested in working on these days is the analysis using computer vision to analyze chest x-rays to diagnose COVID-19. And now it's much harder to access the data, right? This data isn't just up on millions of web pages. And in the early days of the disease, there were only a very few data sets available. Even today, now we have several thousands of images. But if we compare that with ImageNet and modern computer vision, they're accustomed to working with millions of images to get enough variation to really pull the signal from the noise. And early people that were working on, or in the early days of working on COVID chest x-rays, I illustrate some of the challenges. Obviously, we needed experts to label the images, and that was less of a problem because these images were labeled by the hospitals based on laboratory tests or patient symptoms. But there was a sample selection bias problem. In the early days, the images of healthy patients were actually from a data set of children that had been taken from one hospital, whereas the images of adults with non-COVID-19 disease were from a different hospital, and the images of the adults with COVID-19 were from yet a third hospital. And so I've kind of mocked this up. These are fake data here. But if you give this kind of training data to a machine learning system, does the machine learning system discover which patients are healthy and which ones have COVID-19, or is it just discovering which hospital the image came from? And this is a kind of sample selection bias, a very severe one, because we have an aliasing effect or a confounder between the hospital and the disease. And there was work on, I want to mention by this paper here that came out in arXiv just a few months ago, showing that indeed, even if you blocked out the middle region of these images, computer vision algorithms were quite accurate at predicting which hospital the image came from. So they weren't discovering useful disease diagnosis information at all. So that's a big risk that we run in when we use data. We have to get the right data. And that brings me to the final topic that I want to mention, which is the problem of majority bias. So many of you may be aware of the work of Joy Buolamwini and Timnit Gebru and their colleagues at MIT and Google and Microsoft, showing that several commercial face recognition systems were much less accurate on Black faces, and especially on the faces of Black women, for purposes of face recognition or predicting whether it was a male or female, things like that. And this was later confirmed by the U.S. National Institutes of Standards and Technology. And it's gotten quite a lot of coverage in the press, and very recently has led to several of the large providers removing their products from the market. Now, one cause of this is insufficient training data. As I say, these systems were developed in the United States, and they had used samples of images of adults from the United States. And therefore, Black people were underrepresented in that sample, and Black women were an even smaller minority within that sample. And so the accuracy of a machine learning system depends on how much data you give it. And so the system is much more accurate on large majority population and less accurate on the minority population. And this happens in every machine learning application. You need to think very carefully about the representation and all the different subgroups or market segments that do you have enough data to be accurate in those. So the challenge then, to summarize this part of the talk, is that a major limitation for the broader application of machine learning is the lack of good data sets. We need data sets that are representative of the full range of variation in the population, data sets that are accurately labeled, and data sets that actually oversample minority populations. But that by itself, although those are all very critical, is not completely sufficient. The other thing is that these machine learning algorithms need to have the ability to measure their own uncertainty. So an ideal algorithm would, if we had shown it a picture that was of a Black woman, it should have said, I'm sorry, I don't have enough data to accurately classify this image, so you'll have to do it yourself. And we'd certainly want a system that was looking at chest x-rays for COVID to be able to say, that one doesn't look like any of the training data that I had, so I need you to have a radiologist handle that image. And so that's one of the areas of research that we're looking at now, is how can a system know its own limits and then enforce those so that when it makes a classification decision, it has a very good chance of being correct. Another challenge is that machine learning systems are based on the assumption that the training data is a good representation of what the system will encounter when it's actually operating after it's deployed. But in the real world, the properties of the data tend to shift over time. It could be the instruments that change, or as we saw in the TOMO example, the sensors get older, they get dirty, they break. And the underlying phenomenon may change. So the way that COVID-19 shows up in X-rays may be shifting over time. I'm just using that as a made-up example. But and so we need machine learning systems that can detect what we call data shift and respond to it appropriately. So those are the kind of the research frontier right now in machine learning, is uncertainty assessment, being able to reject a query and say, I'm sorry, I can't handle this one, and being able to detect data shift. So in conclusion, I've tried to give you a little bit of a sense of how machine learning is enabling a wide range of exciting new applications. And I gave some examples from weather, from dengue, from wildlife poaching. I would like to point out that there are very good machine learning tools that are available and easy to learn. So there's a huge amount of tutorial information online, and very user-friendly tools. So the company I'm involved in, BigML, you can go to bigml.com and get a free account and start doing work in machine learning immediately. There's the statistical package R, which I love greatly, scikit-learn for those of you who are Python fans, PyTorch, and TensorFlow for doing deep learning. But the full potential of machine learning is limited by the lack of high quality data and by machine learning algorithms that cannot measure their own uncertainty and detect data shifts. So I will stop there and we can move to answering questions. Thank you very much.
Tom, if you stop the screen share, you can see the questions.
Okay. Stop screen share. Okay, so the first question I see is, does unsupervised learning require data to be labeled? So unsupervised learning, as the name implies, is we do not need labels. But if I showed you a bunch of x-rays, how would you know which ones are from the COVID-19 patients and which ones are from healthy patients? The most you could do is perhaps try to cluster them together. So unsupervised learning can be very valuable. For example, when we are doing anomaly detection with our weather data, we can make the assumption that most of the weather observations we're getting are accurate. And we can try to learn what sort of normal looks like in weather data. And then we can signal that a reading that is very unusual, that's when we can flag and call it to the attention of the weather expert. Another question, perhaps. So this is a question about what we call ensemble methods, where you can you don't learn a single machine learning model, but actually maybe 10 or 100 or 1,000 different models, and then you compare them to each other. And this is a very good way of assessing the uncertainty of a machine learning system. So the answer is yes. If you have a set of votes from many different systems and they disagree with each other a lot, then that really tells you you don't have you don't have enough. They've all been trained on the same or very close, very similar data. That data is evidently not sufficient to give you a good best answer. And there are related techniques that come out of Bayesian approaches, which also give you these a large collection of models. Will machine learning replace a teacher or a school? I don't think machine learning will ever replace a teacher or a school. In fact, I mean, machine learning is more like replacing a student, right? We teach our computers by using machine learning techniques. But a big challenge, I think, there is that humans are much better at learning from data than machine learning systems are, in the sense that when a human student approaches a problem, they know a whole lot more about the context, the world, and so on than our machine learning systems do, because our machine learning systems start with very, very little knowledge at all. Okay, so how can we reduce or eliminate the biased analysis using machine learning, since someone has to write the codes? So I think writing the codes of the machine learning system, that by itself, for instance, in the computer vision algorithms that were the computer vision machine learning algorithms that were used in the face recognition, those algorithms were in some sense, they didn't have any built-in bias about race, for instance, or male versus female. But it's the interaction between the algorithm and the data set that leads to that. So the algorithms were focused on the statistics, which leads them to have that majority bias, because the more common case is the case the algorithms are able to do better. So it's more the whole idea of using statistical learning is what creates the majority bias, and different machine learning algorithms would all exhibit that bias, and we are trying to, for instance, you can do some sort of a segmentation or partition of the data into data for different groups, like black people, black women, white people, white males, and so on, and then use only the part of the data that's relevant to the person. So if we gave the system my face, we would want, I don't know, older white males with beards, and just use that data to do the identification. And that way, the information about the majority wouldn't dominate over the minority. So those are the kinds of techniques we can try to use. But it's not that there's a bias, I guess, in the programmer that that they were, racist or something. It's more that we have to think not only about the code, but about how it interacts with the data, and how the code and the data, how they arise in the broader society. So the machine learning class. There are a variety of online courses you can take. Many people like I think it's the Coursera course that Andrew Ng wrote, that's a sort of introduction to machine learning. The Big ML, we also have a lot of educational materials, I guess that's all I dare to say at this point. But there are many good resources out there. So teaching an AI system to be creative. I think it's sort of yes and no. So again, most of the uses of AI for creativity are really using the AI as a kind of tool with the human. So one of the things that was really surprising to me was when people started building these computer vision systems using machine learning. And you could say teach them to recognize, I don't know, cats, for example. You can then you have now a program that takes as input a picture of a cat and outputs, it's a cat, it's a cat. You can, in a sense, run that program backwards and ask it, start with a blank image and make it, and change the pixels in the image to make this image the most cat-like cat you've ever seen. Or you can start with an image of a cathedral or of an automobile and say, make that car look more like a cat. And artists have used this. This is a technique known as Deep Dream that came out of some folks at Google. They've used this as a tool to create just amazingly interesting images. So it wasn't really that we taught the computer to be creative. It's more that people used the computer to be creative. In fact, I would say machine learning has a risk of being actually uncreative, because in some sense it's just regurgitating the past. It was trained on training data, and now at prediction time, it's going to just use that. It's going to prefer to see things that look like what it saw in the past. So some people would say that a statistical machine learning is inherently conservative, so for instance, it can make a car look very much like the cats it has seen, but it can't imagine a new kind of cat that it's never seen. People are using this also in materials design and drug design and so on. So you can, the computer can help you imagine new things that kind of fill in the gaps between things that it had already seen, interpolating, you can use AI systems to kind of like a bit of a blender to combine ideas and techniques from different areas to create something new. Is operational research important for machine learning and deep learning? There's a very close connection between the work that's going on in operations research with all the optimization techniques that have been developed there, and work in machine learning. The machine learning folks are consumers of the operations research techniques. There's an area of machine learning called reinforcement learning, which is designed for solving sequential decision-making problems. So for instance, when we're planning how the game wardens should patrol through the park, that's a very much a kind of operations research problem, to design a good path that meets the various constraints that have to be solved. Okay, is there manual technique orientation for scientists who train machines? I would say there's not enough, both in traditional statistics and data science programs and in machine learning. There's far too much of an attitude of, where does the data come from? Well, you download it from this website. And not enough thinking about, well, exactly what was the social and institutional context around which this data were collected. A very painful example of that is these attempts to do predictive policing. So you can think that the game warden example that I gave is kind of an example of predictive policing. We're trying to predict where will the poachers be, and then send our law enforcement officers to be there. But if you collect data, for instance, only from criminals that were in people that were prosecuted and convicted in a legal system like the one in the U.S., which has strong racial biases, then you get a predictive policing system that predicts that, say, black people are much more likely to commit crimes than white people, when the reverse might actually be the case. So that's another good example of sampling bias, and it's another good example of trying to take a pattern that's true in the past, in this case a racist pattern, and reproduce it in the future. And so I think the field of machine learning has a long way to go to really do good training in the sampling theory and what's known as measurement theory, how the data are actually being collected, and what is the broader social context of that. And there's also a problem on the other side, which is that when you deploy the system, it causes changes in the world. Are those changes that we want or not? So what will be the impact of the sort of sociological, psychological impact of deploying an AI system, and how does that interact with human weaknesses and social and governmental shortcomings? So these are all huge challenges, and we, as engineers, we're constantly need to think about a bigger and bigger picture. Our problem is not just to classify this little individual image, but to think about its much broader impacts. And that requires collaborating with sociologists and anthropologists, psychologists, lawyers, and so on, because they have the mental frameworks, the intellectual capacity to think about those kinds of issues. Okay, well, I'm told time is up. So I'll just thank you all very much for your attention. It was a lot of fun to talk with you, and you can chat with me here or on Twitter. I'm at Dietterich on Twitter. Bye-bye.